I want to talk a little bit about tree diagrams. And given that we are talking about conditional probability and things like independence, tree diagrams in that setting actually do become quite useful. Um, and give sort of a pictorial illustration of the idea of conditional probability. So let's look at this problem. We have 5 red balls and black balls in an urn or a jar or something, and we pick 2 balls out without replacement. And that's already a hint that non-independence is probably going to come up. What's the probability of getting 2 red balls? So the first way, the more down-to-earth way from what we started out with is just say, what's the sample space? Sample space is all ordered pairs of distinct balls. And here, even though we don't really care about the difference between the red balls and the black balls, nature knows the difference. And the fact that we do it without replacement is relying on the fact that these balls are distinguishable in principle. And so what we're going to have to do is say things like, it'd be like the third red one and then the second black one. Okay, so I'm denoting that there's 5 red balls, and I don't care about the difference, but there's a difference. So maybe we could actually put numbers 1 through 5 on the red balls and 1 through 3 on the black balls, and then this would be one particular way they could come out. Okay, so let's see how many there are going to be. So number in the sample space is going to be, well, there's when I'm just looking at all the distinct balls and I'm not caring about the color, there's just 8 balls. And so there's 8 choices for the first thing, and then it's without replacement, so 7. So 56 possibilities in the sample space. Okay. And then what about the event that we care about? That's red, red. Okay. Let's call that E. And let's figure out how many things are in that event. Well, in E, then that is the same number of ways I can pick as if the black balls weren't even there. So that's a pretty common thing, is to get just red ball both times. It's just the same thing as if the black balls weren't even there. How many ways can I pick out and happen to get 2 red balls, a red ball for each thing? Well, that's going to be 5. 5 ways. There's 5 of those red balls to get on the first one, and then 4 for the second one. Okay, and so that's 20. And so it seems like the probability, and this is correct, the probability of getting E, the 2 red ball possibility, is 20 over 56. Okay, which simplifies a bit. I can take out a 4. That's 5 over 14. Yeah. Okay, so now here's another way, which is slightly more sophisticated, but really in a way more intuitive. We draw a diagram that kind of goes by the stages here. Let's just care about the probability of the first choice. Since there's 5 red balls out of 8 total, the probability of getting a red is going to be 5 out of 8 on the first one. Okay, and now I extend that tree to be the 4 possibilities with red, red up here, and red then black here, and let's say black then red here, and black, black here. Okay? So I want to figure out the probabilities. We can actually pretty easily figure out the probabilities of all of these, but I'm concentrating on red, red right now to compare with my previous calculation. And so what I'm going to do is on these lines, what I'm going to do is put conditional probabilities. Given that I've already drawn a red, what's the probability of getting another red? Given that I've already drawn a red, what's the probability of getting black, etc.? Okay? And so what's going along these lines are going to be conditional probabilities. And our law for getting an actual probability is going to say we're just going to multiply things along the lines to get the probability of each branch of the tree. It's going to be a very nice pictorial representation of that idea. So if I've already picked red, now we have to pay attention to that. That's a conditional probability. Now we've got 4 red balls and 3 black balls. So it's going to be 4 out of 7 here. So the probability now, this conditional probability, is going to be 4 out of 7. And then the probability, while we're at it, of getting a black ball is going to be 3 out of 7, the remaining. And then let's go ahead and go fill out the whole tree. If suppose I got a black ball, and so I've got a 5 and 2. Well, now getting a red is quite probable. That's going to be 5 out of 7 here. And here, this probability down here, let's see if I can squeeze it in right here. That's going to be black. Well, let's see. There's only 2 black balls left. That's 2 out of 7. Okay. So that's all the conditional probability. So everything on this line, on this column, this very shaky column, is a conditional probability. And so let's see if we can figure out the probability of red, the actual unconditional probability there. So that's going to be the probability of getting red is our fundamental, one of our fundamental laws for conditional probability is the probability of whoa, I didn't mean to do that. Probability of red. Well, that's an intersection. That's really red first, so I'm going to decorate it. Intersect with red second. Okay, that's what we really want. And that's E. I was calling that E before. Okay, but now we're highlighting the fact that it's an AND condition. Red first and red second. That's the probability of that I get a red second given that I've got a red first. Ooh, he's mismatching my parentheses here horribly. Times the probability that I got a red first in the first place, as it were. Okay, that's this law of conditional probability. That just comes from the definition. That you calculate how likely it is to be on this branch of the tree in the first place. And then you look at the probability, given that I'm on that branch of the tree, what's the probability to go further on this branch? It's kind of a nice pictorial setup. If you multiply those numbers, supposedly we're going to get the right answer. Okay, and indeed, what do you get? You get 5/8 times 4/7. That's the conditional probability is the 4/7, and you multiply that by 5/8, and that's exactly what we were doing here. We just do it in a slightly different way. We do the fractions first and then the multiplication. Here we do the multiplications first and then the fraction. But it still turns out to be 20 over 56, or if you simplify it, 5 over 14. Okay. So, for example, the probability of getting a black and then a red would be the product of these two numbers, 15 over 56. Okay. And that's interesting. It's the same as the probability of getting a red and then a black. That's also 15 over 56. And so that's interesting that it doesn't seem to depend on the order, even though we're paying attention to the order. That's an interesting thing to think about. And black is the least probable. That's going to be 6 over 56 because you're getting down to where there's not very many black balls left. Okay, so that's an illustration of how the tree diagram helps. So let me clarify something. This kind of tree diagram is different from the one I introduced briefly before. There's two kinds. A tree diagram, in one case, can be basically a systematic listing of the entire sample space. This is not that kind of tree diagram. Okay, these 4 things I've labeled here are not a sample space for this experiment. It's really important. Sample space, we only think of a sample space as something where the probabilities are equal, so that we can use this fundamental principle of taking the number, the number of an event over the number in the sample space. That worked. Okay. This is a listing of 4 events that we care about. But it's not really a complete listing of the sample space because it doesn't distinguish like red 1 and then red 2, or red 3 and then red 4, or red 1 and black 2, or red 1 and black 1. And it would need to distinguish those if I could just apply the straightforward counting principle. It's a more sophisticated kind of tree diagram where I only list the events I care about, but then I have to be much more careful about what the numbers are here. And I have to do probability calculations for each of the branches of the tree. Now, they weren't hard probability calculations, but they were calculations that we're not just counting, oh, 1, 2, 3, 4. Oh, there's one way to get there. The probability is 1 out of 4. That would be an incorrect calculation for this problem. And so that's an important distinction between the types of tree diagram. This kind of tree diagram is much more useful than the other kind because it allows you to only focus on the events you care about as long as you understand this idea of conditional probability and the idea that they multiply to get a real probability. Okay, so you're going to be trying that out in the homework problems, a few of them, and hopefully this should be good enough.